Hey, welcome to the Art of Code. My name is Martijn, and what you see behind me here is a Koch curve. And while on its own it might not look terribly exciting, it is an example of a type of fractal that can be used to make many cool things, like leaves and trees and the trippy visuals that you see here. And so I thought I'd make a video about it. So if that interests you, stick around. So the way this works is actually quite simple, or at least the idea behind it is quite simple. We start with a simple shape, and now what we're going to do is for each line segment of this shape, we're just going to replace each line segment with a copy of the entire shape. So where this line segment is, there's going to be a little hat, and here's going to leave hat, and there and there. So if we do that, then we would get something like that. And now we just did that again, so each line segment is going to be replaced with a little hat. So then we get that. And we keep doing that until we have something like this. And so that's the basic idea behind this curve. And so let's try to make this. And so let's first try to get to this point over here, where we just have a straight line with a little hat in the middle. Right, so I have here a brand new shader toy. Let's clean it up a little bit. The first thing I'm going to do is I'm going to make it so that the origin is in the middle. And I'm just going to account for the aspect ratio. Then I'm going to make a black screen. So I'm going to just return 0 for everything. So there we go. And like that. So that's my brand new shader. And the first thing I'm going to do is I'm going to draw like the bottom of this shape, which is a line segment. And for that, I'm going to get the distance between the position of my pixel and a position on the line segment. And let me just write it out and I'll explain it. So uv.x, let's say minus 0.5 and 0.5. And then my line segment is at resting at y equals 0. And let's look at that. So col plus equals d. Okay, and so you can kind of see the line here. Let me zoom out a little bit to be able to see it better. So there is my little line segment. And the reason why that works is this is my position of each pixel, and this is the position, the closest position on the line segment. And so the line segment is lying on the x-axis where y equals 0. So that's why my y component here is 0. And then my x component is either the x component of where my pixel, or if I'm outside of the boundaries of my line segment, then it gets clamped. And so that's how that works. And so let me use that to cut out a little, an actual line. So let's say 0.0, and let's see what that looks like. Okay, so there's my line segment. I want my line segment to go from -1 to 1 instead of minus 0.5 to 0.5. All right, there we are. And the first thing to realize is that the entire shape is symmetrical around the y-axis, right? So around the middle, it's the same on both sides. And so for that, I would want to fold over half of the screen so that I only have to worry about half of that shape. And before I fold over, let's just visualize the UV coordinates as well so that we can see what we're doing. And so I'll just do that. And so here I see the UV coordinates. They have their origin at the middle. And as the x increases, my red increases, and as the y increases, my green increases. So that's how I can visualize this. And so now let's fold over the negative part of this onto the positive part. And for that, I can just take the x component of the UV coordinate, and the x component of the UV coordinate is going to be negative on the left side of the screen. And I'm going to say, well, take the absolute of that. And so any negative number is going to be folded over onto a positive number. And so the line didn't change because my line went from -1 to 1. But you can see that the UVs have changed. So now the UVs are symmetrical along the center line. Okay. Now, one thing to realize is that this hat, this entire shape, is 3 units long. Or yes, like it has a flat line on one side, which is 1 unit. Then it has the hat in the middle, which is also 1 unit wide, and it has another flat line on the other side. And my line here is only 2 units wide, right? It goes from where my x equals 1 after my mirror, right? My x equals 1 just goes from 1 to 0, and then from 0 back to 1. So it's only 2 units wide. So let's make it wider. And I can do that by just subtracting 0.5 from this. So like basically I want to add 0.5 on both sides of the line so that the entire line segment is going to be 3 units long. And the reason why this works is because right now my line goes to where it stops where my x equals 1. But if I subtract 0.5 from it, then this point will only be 0.5. And where it is 1.5 right now, that will be 1. So that's why this will widen the entire line. All right, so now we have the line, like the baseline, and now we want to bend it at certain places to kind of pull that hat out of the line. And for that, like it would be nice if we could use a reflection similar to how the absolute is a reflection around the vertical line, to have a reflection around an arbitrary line so that we could just put a line here at a let's say 45-degree angle, or whatever the angle ends up to be, to reflect around that line. We don't have a function for that, so we have to make one. And so let's lay this to rest for a little bit and work on that function. So I'm just going to take this out. And we're going to build a function that can reflect a point around an arbitrary line. And so for that, I'm going to first make a vec2, call it n for normal, that indicates the orientation of this line. And the orientation is just going to be the sine of an angle and the cosine of an angle. And so the sine and the cosine of an angle, they will just trace out a circle, right? So my n vector will just be like the hands of a clock, like around the clock in whatever direction we want. And I want to be able to control that. So the angle, I'm going to say, is my x position of the mouse. And I don't have the mouse yet, or at least not like this. So let's make that as well. So mouse equals I mouse, which is what Shader Toy gives you, .xy, divided by I resolution .xy. So the I mouse is the mouse position in pixel coordinates. And so we have to normalize that in order to get that in the 0, 1 range. Okay, so now let's get the distance from any pixel to the line that is described over here, or the line through the origin, I should say. And so for that, I'm going to get the distance. I'm going to use a dot product. So a dot product between the position, my UV, and the line normal. And let's visualize that. Plus equals D. Okay, so now I have the distance to an arbitrarily rotated line. Okay, and let's try to get some really quick intuition for why that works like that with the dot product. So over here, when my x is all the way 0, then basically this is going to be 0. So then over here, I'm going to get the sine of 0, which is 0, and the cosine of 0, which is 1. And then over here, I take the dot product, and the dot product is just the components multiplied together and then added up. So it's basically this times n dot y. That's what a dot product does. In three dimensions, it would also have a z component as well. And so, well, here if we fill in this 0 and the 1, then we get uv.x times 0 plus uv.y times 1. And so that is just uv.y, right? So this is the same as this. Okay, and similar for the x direction. So if I was halfway here, then I would have 1/2 pi well, the sine of that equals 1 and the cosine equals 0, so then it's flipped around. So I hope that gives a little bit of an intuition of why this works. All right, so let's cut out a line. Oh, and also, by the way, so this gives me the distance, and over here it's black because we're on the line, so the distance is 0. And on the left side of the line, it also gives you the distance, but it gives you a negative number. That's why everything is black over here. And also, let's be able to, because right now I can only rotate this far. So let's just multiply that by pi so that we can at least rotate 180 degrees. So now I can rotate all the way from here to here. All right. Okay, so let's cut out a line for this. So for that, I'm just going to take the absolute, and then I'm going to use the smooth step trick again. So 0.01 and 0.0. Let's say, okay, so there we have a line. And now we want to make something that can reflect points across that line. And for that, let's think about it. So let's say we have a pixel over here. Well, we already know the distance to the line, which is this d value. And we also know the direction. Oh, I clicked here. We also know the direction, which is this n value, right? Or minus n. So if I'm at any position, at any UV, and I go in the direction of n, like d steps into that direction, then for any pixel I would have walked right to the line. Okay, and now I don't just want to walk to the line. I want to take one step to the line and then another step to be on the other side of the line. So for that, I just multiply this by 2. And let's visualize this. So let's just visualize the UV coordinates. So plus equals UV. And so now I see my UVs here that are rotating with the line. And it's a bit confusing to see what's going on. And that is because pixels on one side of the line get reflected to the other side, but pixels on the other side get also reflected. So it's basically like flipped around that line, and that's why this is a bit confusing to see, because what we really want is we want to only flip one of the sides and not the other side. And luckily that's quite easy. I said before that this d, this distance value, is going to be positive on one side of the line and negative on the other side of the line. And we can make use of that because we can just say, well, give me the minimum value of d and 0. And so in this case, if my d is larger than 0, then this thing is going to return 0, and so it will cancel out because this entire thing will be 0. So this will make it that only one side of the line will be reflected. Okay, so now we only have one side. And if you wanted the other side, you can just make this max, and then it will reflect the other side. Okay, but in this case I want min. All right, so let me just play with these UV coordinates a little bit just to be able to visualize a bit better what's going on. Okay, so now we made a function that can reflect a point around an arbitrary line. And you can see how that is good to bend a line so that we get that hat in the middle, right? So let's go back to where we were. Let me just see here. Let me put comments around this and then take the original comments back out to get back to where we were. Okay, so that's where we were. And now we want to bend that line around this point and around that point. And so let's take the bending code over here. Okay, so we have this d value here. Let me just substitute this d here so that we don't have to have it separate. So let me just take this. I'll just take that and I'll put it here. Hang on. I take it from here and I put it here. Okay, and now I can just take one line of code here to do this bending business. All right, so here we mirrored around the center, right, around the vertical axis. Here we kind of shifted the line segments out a little bit, and now after that we're going to bend around the origin, right? And the origin is over here, and it's also over here. So let's see what that does. Would you look at that? So now we can bend that line. Awesome. All right, so now let's bend that line exactly as far as it needs to bend, which is right about here, right? And remember, so I'm putting my mouse X into this formula, and so my mouse X goes from 0 over here to 1 over here, and so these lines touch right about here, and so to me that looks like it is 2/3 from the left here, or 1/3 from the right. So let's put that in. So instead of my mouse.x, I'm just going to say, well, give me 2/3. And I just compiled that. And by the way, compile, you can press Alt-Enter. That's what I'm doing. So you don't have to go down here and click play each time. You can just do Alt-Enter. So now we have that hat. Great. So let's clean this up a little bit. So now the next step is to replace each of these line segments with this entire shape. And that might seem like a daunting task, but it's not as bad as it looks, because if we can manipulate the UV coordinates for each line segment so that the UV coordinates are the same as they were all the way in the beginning, then we could just do this entire thing again. So how can we get the UV coordinates back to the way they were? One thing to realize here is that our entire shape is 3 units wide, right? There's 1 unit here, and there's 1 unit here, and 1 unit here. And we want to paste that entire shape inside of, let's say, this line segment here. But this line segment, if I look at the UV coordinates right now, at the red here, at the X, that is only 1 unit wide, okay? Because it goes from 0 to 1 over here. But I need 3 units of space. Well, for that, it's simple enough. I could just multiply my UVs by 3. So now, and I didn't compile it yet, but now it would go from 0 all the way to 3. So that already gives me enough space. But now I also want the origin in the middle of the line segment and not at the left side. So for that, I can just subtract 0.5 from the X coordinate. And that would reset my UV coordinates, and I will compile. It's a bit hard to understand here now, but now basically my UV coordinates are reset to do another one of those hat folding exercises. So now I can just copy this entire thing and paste it underneath here, and watch what happens. So now I folded my entire, I folded it in such a way that we can fit a hat in each line segment. And we can do that as many times as we want. So we can just reset the UV and do the fold again. So we can just copy paste that here, and that will keep going. The only thing is that my line gets smaller and thinner and thinner, and that is because each time I multiply this UV here, I'm kind of compressing space, and so I would have to compensate for that. So here I multiply by 3, and then I multiply that whole thing by 3 again. So here I would have to divide by 9, right? 3 times 3 to get the same thickness, basically. All right, great. So now let's put this entire thing, because we could copy paste this as many times as we wanted, but it's much nicer to put it in a loop. So let's put it in a loop. So I'm just going to go here for int I equals 0. I is smaller than a number of iterations, and then I++. And we're going to stick that in there, and then we can get rid of all of this extra stuff here. And also let me change the indentation. Okay, so let's look at that. And then it looks like it broke, and that is because the last time we get through this loop, we should not do this, right? And what I found the easiest is, instead of putting this at the end of the loop, we can put it at the beginning of the loop. So put it over there. And well, then we still have the same issue, because then the first time we get through here, we don't want to do this. But that's easier to undo, because here we're multiplying the UV by 3. Well, if I take this initial multiply out, then that cancels out the first time we get in there. So let's see what that looks like. So now you see they touch again. It's just that they moved over from the center, and that is because this thing has to be compensated for. So we can just put that in front of here, and then instead of minus, we can say plus. And then one thing, because if I do this right now, it's still at the wrong position. And that is because this here is done after we multiply by 3. Okay, so like in other words, this offset is 3 times too large if you do it before. So we have to divide by 3 in order to get that back in the middle. All right, so let's get rid of the UV coordinate over here, and also, so here we're dividing. So here we're dividing by some number here. Let's make that more flexible. So I'm just going to take floats. I'm going to make a scale variable that keeps track of how many times we compress the UV space. So each time we multiply the UV by 3, we also multiply the scale by 3. So that in the end I can just divide by scale. And then it doesn't matter how many iterations I do, it will always be the same thickness. Yeah, and then also over here, so over here you could change the thickness of your line, right? But a nicer thing to do is to make it resolution independent by doing this. 1 divided by I resolution dot y, let's say. So this ensures that it's always 1 pixel thick, no matter if we zoom in or not. So if we go full screen, it will still be 1 pixel thick. Yeah, okay. So that is a good moment to sit and have a sip of tea and and talk about the previous video that I did about Truchet tiling before we get to the bonus time on this one. So in the last video, like at some point I said that for the UV coordinates on the tiles, that the Y coordinate would have to be flipped because otherwise you would get discontinuities. I was wrong, and many of you pointed that out. And so so for quad Truchet tiling, in this case, this is possible. And thank you guys for pointing that out. Like the solution is quite elegant. You can see it here. It's only a few lines of code to do that. And yeah, so thank you guys for that. All right, so let's see what else we can do with this thing. So this is called the Koch curve. Let's take 3 of these curves. So right now we have 1 curve in the middle, but let's take 2 other curves and stick one over here and stick the other one over there to make this into a Koch Snowflake. And so for that, we can just use the same reflection trick to, like, imagine you had a line over here that's right on the end that goes like that to reflect this entire thing over to the bottom, and the same thing on the left. Then you could get a snowflake. So let's try to make that. And so for that, we're going to do a different angle here, and for that, let's just put this in its own function so that it's a bit cleaner. So I'm just going to cut that out. I'm going to call it n of angle, and then over here I'm going to say vec2 n, and it's going to take as an input an angle, and then as an output it's going to just return a vector that is pointing in that direction. And so this shouldn't change anything. Okay, it doesn't. And now let's just take this here and put it inside of here, and let's put this entire thing down here so that we can screw around with the angle beforehand, and then we will not screw with the with the curve itself. And so now let's see here. Let's take the code for reflection, which is this piece over here, and let's put it over here. And let's take, yeah, let's just get rid of this angle here now. We don't need that anymore. And let's put the mouse back in to see what we're playing with here. Okay, so now I'm reflecting around around the origin, and actually perhaps I should visualize that. So let me just take this back out, call it D, and then I just do float D equals this. So that shouldn't change anything. Oh. Okay, I'll get rid of that over there. There we go. Let me just visualize this. So I do col plus equals smooth step of the absolute value of D with some thickness, 0.01, 0.0. And so now we can see what we're doing here. So we're reflecting around that line. And so I don't want to reflect here, I want to reflect around here. And for that, I can just remap my UV coordinate before I put it in the dot product. So I can just subtract the point from it where I want the origin to be. And so over here, you might think that is 1.5, but it's actually 0.5 because we're multiplying by 3 over here. So this is 0.5, and it's on the x-axis, so it's at 0 high. And let's see. So now my line moved over there, and now it looks like it broke, but it didn't. It's just reflecting the wrong side right now. And so I said before for that. So right now it's only reflecting where the D is negative. It should reflect where the D is positive. So I could just make a max over there, and now I have the other side. Cool. All right, so now I could do this whole thing on the other side, but there's a simpler way of doing it because this entire curve is symmetrical along the y-axis, and so for that I can just go, I guess, over here, and I could just reflect the x around the y-axis. So abs uv.x. So that will just reflect. Now, similar to how we did before, we have to figure out at what exact angle these lines touch. Let me just zoom out a little bit. So UV times equals 2, let's say, so we can see. So these lines touch over here. So so a good guess would be, let's say 4/5 from the left side of the screen, 4/5. So let's go over here and say, okay, give me 4/5, and that's wrong. So my next guess would be 5/6. So 5 and 6, and now they touch exactly. Cool. Now my flake got moved down a little bit. Well, actually it didn't, but like because the original curve was like lying on the 0 line, this needs to be shifted up a little bit in order to get to be in the middle, and the way to figure out how much is, well, you could think of a triangle that goes from here all the way to the end here and then down here. Okay, so this triangle, and that triangle, if you remember from high school, there's this distance. This is the y distance that we need, that we want to know in order to know how far up we need to shift this thing. So let me see here. It's the tangent of the angle. So the tangent of this angle. Well, the tangent of the angle equals y divided by x. And so y is the thing that we want, and x we already know that's 0.5. And so if we multiply both sides of this equation by 0.5, then we get that y equals the tangent of the angle times 0.5. And that is how far we need to shift this thing up. So let me see here. So we could say uv dot y minus equals the tangent of this angle times 0.5. Let's see. Okay, that's the wrong direction, so just plus equals then. Okay, and now we're back in the middle. And now we can get rid of the extra lines and zoom in a little bit. 2, 5, 1, 2, 5. Okay, so there we have the Koch Snowflake. I did it with 3 sides. You could also do it with 4 sides, perhaps, but I'll leave that up to you. All right, now one thing to realize is that we are still, even after all this time, and well, maybe I should do like a few less iterations. Yeah, okay, like this. Even with this, we're still only drawing one line. We're only drawing one line, because what we really did, instead of dealing with drawing many lines, we kind of worked on the space. We folded space. We folded space in such a way, and many different ways, so that one line turns out to be this, which is, to me, completely mind-blowing. Yeah, so, and this is also, and yeah, let me, because my UVs look a little bit saturated right now, let me just also divide my UVs by scale as well, so that we get that. And this whole space folding business is something that happens a lot in shaders, and that is probably also what is kind of difficult for people when they first start, because you have to look at a problem from the other direction completely. But it's also super powerful, because as you can see, like, we just folded space and we just drew one line. Because we folded space, we can draw. We don't have to draw a line. We could draw whatever. So I encourage you to try drawing different shapes in this crumpled up space. One thing that we can do is we could sample from a texture. So let's do that. So instead of adding my UV or visualizing my UV coordinates here, let's just make our UV coordinates like that, and let's just look up from a texture. So I can say col plus equals texture, and I channel 0, and then my UV coordinate dot RGB, and then I have to add it. I have to add a texture. So I'll go over here, and let's pick this texture, and let's see what that looks like. Oh boy, let's multiply that times 2. That is pretty cool. Let's add I time to this, times 0.03, let's say, to make it move, and let's go negative here. And so you can see that this is quite powerful. You can do cool things with it. I don't know why my texture is low resolution. Maybe it's because of the screen recording software. If you follow along, then this should be a bit sharper than what it looks like right now on my screen. But yeah, so that's that. And the cool thing is that you can screw around with this. So this is called a KIFS fractal, and KIFS stands for kaleidoscopic iterated function system. Kaleidoscopic because it's kind of like a kaleidoscope. We're reflecting points. Iterated because we have a loop over here, and function because we're iterating a function inside of here. And there are many different versions of KIFS fractals that look like ferns or trees or yeah, like different things. And you can play with this. You can play with all these parameters to get different shapes. So let me just, yeah, over there. Let me just show you one thing you could do. So over here, this is the angle that we determined for the shape of the hat. But we can choose a different angle. So let's add the mouse to this so that we have some control over this. And now you can see that we have full control over that angle. And you can see we can add many different cool looking things. Let's look at this full screen. So yeah, so this is quite powerful. You can do a lot of cool things with this. If you check over here, for instance, if you go a little bit farther, you'll see something that maybe looks familiar over here, right? So you might look, that looks like maybe an upside down Triforce, but it also looks like a Sierpinski triangle almost. And that is because Sierpinski triangles can also be made with this same type of algorithm. So yeah, if you made it this far, then I take it you like my video. So that's great. If you make something cool with this, then post it in the comments below. And I promise that in the next video I will take some time to maybe showcase what some of you have made. I think that would be cool. So anyways, I hope you liked it, and I will see you next time.